Hello, everyone. My presentation is called From 3D Skeletons to Walking Events, Detecting Heel Strikes and Toe-Offs from Ordinary Video. Much thanks to my mentor, Johnny, and Professor Garani. Um, and this project was sponsored by iSense. So what is the overall picture of our research? The timing of each step of a human walk provides useful information about that person. It's very useful for certain medical diagnoses, such as looking for certain cognitive impairments. And traditionally, these measurements have to be taken in a lab using specialized equipment such as pressure-sensitive walkways or wearable sensors. So these are not the sort of things that you could have at home. And video-based systems could offer a more accessible alternative to these measurement approaches. A system where you could just take your camera, set it up, and record a video of yourself walking and use that to retrieve your information. And this is pictures of mats and sensors that I was talking about. The lab has already developed a system that takes video and turns it into these 3D skeletons over time using pose estimation. And what I mean by 3D skeleton is I mean kind of a joints moving through time. So like for each point in time, it tells you the 3D location of every joint. So this has already been taken care of. And what we get is a moving 3D skeleton. But the missing step is finding the step events like heel strike and toe off. Heel strike is when the foot makes contact with the ground, and toe off is when the foot leaves the ground. Our research question is, can those things be detected accurately from the 3D skeleton? There are two possible approaches, kinematic methods and machine learning. Kinematic methods use interpretable rules based on how the feet and legs move, while machine learning uses a pre-trained model to recognize events from examples. What does that mean? A kinematic method uses heuristics like the velocity of the foot, the speed in a certain direction, the position of the foot, and extrema, like minimums and maximums of the various time series data of the feet and legs to use certain hard-coded rules to calculate the results of when the predicted events are heel strikes and toe offs are occurring. But machine learning does not pre-code its patterns. It has the machine infer it from a very large set of data. And you really do need a very large set of data to do machine learning. So we never trained a model ourselves. We used models that other people had trained on their own data and tried to use that on our data. And each method was evaluated by running it on the 3D skeleton data, comparing its predicted events with events measured by the reference system, and measuring three statistics: timing error, missed events, and false positives. If a method does well in all those three statistics, it's probably a good method. Now, when we worked with the Zeni algorithm, which is one of our kinematic methods, we noticed a major issue. And this issue is for many of our kinematic methods. A lot of them have this issue, which is phase shift. The red represents the predicted heel strikes and toe offs for Zeni that Zeni created, and the blue represents the ground truth. The results, the actual location of the heel strikes and toe offs as collected by our pressure sensitive mat. And what you can see is that the red predictions are all coming in a bit late. And this is problematic because now everything's off. And there's no good automatic way to fix this issue. So the picture is broken, but what was supposed to be depicted here is you see how there's everything's been aligned back over. And this was done by having the human pick out one of the ground truth. The human only needs to annotate one ground truth value per window. And we tested that when this occurs, it is possible to align everything so that it lines up all nice. So you don't have to annotate everything by hand. You only need to annotate one thing by hand. And this is a major advantage in clinical settings. And Zenny and Josowitz, two of the authors of the papers that we drew from, were the best methods. The machine learning methods did not perform well at all. And Zenny and Josowitz were the best kinematic methods. They had low mean absolute error, low false positive rate, and low miss rate. We also showed that our hybrid approach decreases the mean absolute error of Zenny by a very large amount compared to the fully automatic approach where we don't manually annotate anything. And the third bar in the diagram is the theoretical optimum if we had perfect removal of phase shift. Likewise, the miss rate is very much decreased, going from basically unusable in a clinical setting to very usable in a clinical setting. And the same is true of the false positive rate. Zenny also performs better than machine learning. The miss rate is much lower, and you can see the bar is it's just a lot less. And then the false positive rate, it's the same story. Zenny is performing a lot better. So we think the reason why this is happening is because, although we can't confirm this, we think it's because, not because like somehow the paper is wrong, because the paper the machine learning that we drew the machine learning algorithm from performed really well. But in machine learning, if the data is different, if you run the model on data that's very different than the data that it was trained on, it will perform poorly. So we got some very noisy output from our machine learning model. Now, some limitations of our process is the data set was small, about 20 subjects, and some published algorithm descriptions leave implementation details ambiguous. So we had to infer what the best option would be for our implementation. Our next steps are to test the more participants in more walking conditions, combine methods. So Zenny performed well, Josowitz performed well, but maybe we could implement the two, we could combine the two so we'd have an even better method. And we could also try training a machine learning model if we had more data. And we could finally create confidence scores to identify predictions that are uncertain so that they can be given more scrutiny if we're going to, for perhaps further manual annotation. That's it. Thank you, everyone. And this work was sponsored through the NSF REU site in Sensing and Smart Systems.